Now what we're going to do is we're going to start vectors. Okay, we're not going to finish vectors today because we actually have part of it comes next week as well. So let's see what we can get through today just so that we have a little bit of breathing room. So here we go. Vectors are, so we have different, we do not have a quiz this week because we didn't have a lecture last week. That's why I opened up the homework last week, because some people were behind on their homework and we didn't have a quiz this week. I just thought I'd let some of you catch up. So here we have different kinds of things. So this first A is just a line. It goes infinitely in both directions. B is a line segment. It stops at P and Q. Oh, excuse me, I'm sorry. And C is called a directed line segment. It starts at P, the initial point, and it goes to the terminal point Q, and it has a direction. C would be a vector. Vectors have direction and magnitude only. Direction and magnitude. Is it raining? Okay, hold on a second. All right. So two vectors are equal if, so V equals W, if they have the same magnitude and direction. So for example, we can say PQ and RS are equal because they're going in the same direction, and if we count x's, we have 1, 2, 3, 4. So we have 4 in the x direction and 3 in the y direction, which is the same as 4 in the x direction, 3 in the y direction, and here we have 4 in the x direction and 3 in the y direction. These vectors are exactly equivalent, even though they start in different places. Like say you had an airplane, and your airplane took off from Miami, and it was going 15 degrees northwest, okay? So this is taking off from Miami. And we have another one taking off from New York, and it's going 15 degrees northwest. And they're both going at 500 miles per hour. I have no idea how fast planes travel, so hopefully that's about right. So we can say that those two planes, that's northeast, hold on. So northwest, say we go 15 degrees northwest, this is New York, this is Miami. Those would, I don't know, yeah, sorry. If I'm acting, I shouldn't probably give an example that I'm not aware of, but I think we can all, I think knots is, I don't know, I think knots is boats, yeah, I think so too. Nautical. So anyway, these are equivalent. Vectors representing these two airplanes would be equivalent even though they're not starting in the same place. Basically, that's all I really wanted to say. Okay? So if we want to add two vectors, and here's vector V, and here's vector W, we do like what's called the head to tail, or tail to head. In my day, that's what they called it. Like the initial point would be called the tail, and the, is that right? Head to tail, head to tail, head to tail. Oh my gosh. So we would start here at the initial point, we'd end at the, and then we put the next one This is, we'll call that the head, and then this the tail, okay? So we always put the beginning, the initial point to the final point. For example, I have this vector v and this vector w. We put them together, and then when we add them, hold on, let me get another color. When we add them, we add the head. The head is actually, this is the, we call this the head, and this the tail. So we add, we go from the head to the tail. So we start at the initial point and we end at the final point, and that's how we add them. Let me get one that's not already done here. Oh, they're all already done here. Let's do this. Let's say I have a vector, we'll call this v, and let's call this 3, and we'll call this 3. It looks pretty even. And let's say we have another vector w, and we'll call this 2 and 3. Okay? So what I want to do is I take this v, and I want to do, what is v plus w? I take this v, and I say, okay, well, there's v, and that's 3 and 3. And then I take w, the beginning, the initial point of w, what we call the head, and we place it right here. And then we have to go in that direction. This is 2, and this is 3. Sorry, I know it's not to scale. My answer, geometrically, when I add those two together, is from the head to the tail. This is v plus w. That final one is v plus w. I think I can do this in Alex. Hold on, let me get an Alex problem here for you. Probably be easier to show you on Alex. It's not an answer, unfortunately. Here, let me do it like this. Hold on. Hold on, I'll find one. Give me 1 second. I haven't found it yet. Geometric. Oh, here we go. Vector addition. Good. Okay, here we go. Oh, pushing the wrong thing. Hold on. Maybe I have to put it over there. Hold on, let me try one more time. Start sharing this. Share. Okay, got it. You can see this now, right? And that's just since I've been here. And that's actually just in the last hour, probably. Can you see my Alex screen here? No? Huh. Are you still seeing me? Oh, you are still seeing my 7 unread emails. Okay. Now you can see Alex, but it's not the right Alex. Darn it. Yeah. I don't know why it won't. I don't want it to show you this one, though. I have another screen open. Hold on, let me figure out why I can't get that screen. Give me one more second. Ah, here we go. I think now. Nope. You can help? I don't know if you can help me. Give me one more second, otherwise I don't know why I can't. I guess I can just close this down. I didn't want to, but now it should work. Yeah, now I had to close all my other screens. Okay, now you should be seeing what I want you to see. But you're not. Okay, one more time. You know what it is? I have 2 screens, and it only likes... Okay, now you can see it. I think I just have to do it on this other screen over here. Okay, you can see this, right? Okay, good. So what I'm basically trying to say is if I want to do vector addition, and what I'm trying to do is add 0.6b. So here I have, this lets me move the vector. So here's my vector. I'm going to start, it says having initial point at P. Okay? And then 0.6, this is 1 and this is 1. Well, 0.6 means that this goes to 0.6. And I used this icon to make it bigger and smaller. Okay? A is 1.2, so I have to make it have a magnitude of 1.2. So far, so good, right? So then what I'm going to do is, remember I said to add it, I have to put them together. So I'm going to put, notice how now they're together. The initial point to the terminal point, and then again, the initial point to the terminal point. Does this make sense? When I add them, I use this icon, and I start at the initial point, and I end at the terminal point of both of those vectors. That last one is the answer to the addition of the vectors. Okay? Did that make sense? Go ahead, Red One. I don't know what you said. We have to add them first. Connecting terminal point to terminal point would be wrong every time. Yeah, no, you don't want to connect terminal point to terminal point. It's the initial point, so we have 1.4s. So first thing I'm going to do is I'm going to move s to the beginning. And then I'm going to make it 1.4. So there's 1.4s, right? Then what I'm going to do is I'm going to move t. T has got to start where s ended. and then that's going to be 1.6. Now, the final answer, now I've just put them together. It says, don't forget to draw your final answer. My final answer starts at the initial point and ends at the terminal point. That line from P to the end of S, that's my answer. We'll do some more on PowerPoint, but I think it's just easier to show you on here because it's nice. Okay, good. I can do a subtraction one too. The subtraction, basically when we subtract vectors, just like when we had, you know what, give me a second. Let's just do some more PowerPoint part and then we'll go back to this. I'll leave it open, okay? So, like you need a little bit of, it's not all just about how to work it in Alice. You do need a little bit of information. Okay. So as you can see, now here it's saying V plus W equals W plus V. Because if I start at V and I go to here, let me get this pointer out. If I start at V and I go here, then I add W on, I end here. But if I start here and I use W first and then I put V on, notice we get to the same point. So it doesn't matter. It's commutative. V plus W equals W plus V. And the same thing with, it has the associative property. It doesn't matter in what order I add the vectors. It just matters that I add them together. Okay? If I have a vector and I add nothing to it, or I start with the zero vector and I add a vector, again, of course, I get my V. Now, this is a lot like polar coordinates. If this is positive V, remember in polar we went the exact opposite direction. That's negative V. Negative V just has the exact same magnitude, but it goes in the exact opposite direction. And if I add V plus minus V, of course, we should get 0. Any questions right now? None? Okay. Onward. So just like when we did Alex, remember we changed, if it was 1.2, we would lengthen it. If it was less, we would shorten it. If we take a vector and we want to, if we multiply it by a scalar, scalar means constant. So I'm multiplying by a constant, not another vector. Multiplying by a vector is completely different. So here, notice, here's V. So it's 1, 2, 3 in the X and 2 in the Y, right? If I multiply by 2, this is 2V, this should go 6. 1, 2, 3, 4, 5, 6. This is 6, and it goes up 4. And it becomes 2 times as long. And again, minus V just goes in the opposite direction. Okay? And okay, good. And here are just the properties of vectors. We talked about most of these. Here, K is a constant, so it can distribute to each vector. It's not a vector. And when we subtract vectors, we can talk about it as adding a negative vector. And these both are constants, so they just act like values. So there's nothing really here. We are not learning how to multiply vectors yet. Okay, so now remember I said it doesn't matter what your position is on a vector, because it can be anywhere in space and it still can be equivalent. But sometimes the best thing to do is to at least start them in the same place. Okay? So we have what's called a position vector, and the position vector just says, okay, let's let's at least start it at the origin so I know where it is, okay? So we have, and every vector, there's about a bunch of different notations for vectors. We can say this is one way we can represent a vector. We can also, when we write V, we can write it with like that over it. That means a vector. With an arrow over it means a vector. What else? What else do they do? There's a bunch of different notations. We'll get to them all. So now, say I have this vector, like here's my vector somewhere out in space, right? This is my vector out in space. Well, I want to put it back to where it would be 0. Well, how would I do that? I can just say, well, I know the length of this vector is, if this is x1, then, and this is x2, it would be x2 minus x1, right? That would be the length of this vector. So I'm just going to now make it, I'm just going to put it right back here. Now the lengths are the same. And the same thing with the y values. Here's my y2 minus 1, y1. So I'm just going to put it back here so I know everything's starting at 0. Okay? So I'll